Alright, welcome back. Doing another example here with nodal analysis to solve the voltage drops and current through each of these resistors. And in this case we have a circuit with two independent current sources. So the very first step that we want to do is we always want to pick a node and ground that node, and that's going to become our reference voltage, basically our zero for the rest of the problem. It helps to pick one that has the most possible branches connected to it, and it also often helps to connect power sources to it. It doesn't give us such an advantage here with the current sources, but definitely when the voltage sources are here, you always want to connect it to a voltage source. But that's not what's going on in this problem, but we're just going to go with this one anyways because it does have 4 branches. Just to make it super clear what's going on here, let's actually highlight all of the nodes a different color just so it's really obvious which node is which. So the blue node we're going to call, let's just call it node A, and then we'll call this one B, and we'll call this yellow one node C. So we have 3 nodes that we don't know the voltage, because right now we only know that the red node has a voltage of 0. So basically we are going to have to write KCL for each of these 3 nodes, and that way we'll have 3 equations and 3 unknowns. Now to get started with KCL, we do need to assume some currents, and it doesn't actually matter which way we write the currents, but let's just label on a few and just assume a direction for them. I can tell you right now that one of these is drawn in the wrong direction, but it's not actually going to hurt our analysis at all, and we'll find out later on which one it is, and we'll just flip the direction and it will be fine. So you don't have to worry about trying to know exactly which direction the currents are going at the beginning of the problem, because that's what the point of the problem is to find out the currents and the directions. So let's just write Ohm's law up here just for reference before we forget. We have V equals IR, and we can also rearrange that to have current is equal to voltage over resistance. And let's pick a convention for current flowing in and current flowing out. Let's just say for currents flowing into a node that we're going to treat that as negative, and currents flowing out of the node we're going to treat as a positive. This will be for when we sum the currents to 0, because the sum of all currents flowing into and out of a node must be equal to 0. So let's get started then with doing KCL at node A. So the way that we've drawn it is that we have 2 amps coming in, we've assumed I1 to be going out, and we've assumed I4 to be going out as well. So when we set up our equation, we said negative is in, so we have negative 2 amps coming in, plus I1 leaving, plus I4 leaving, and that's all equal to 0. You really could just move this negative 2 to the other side, and we could say that the sum of currents flowing out is equal to the sum of currents flowing in. It's the same thing. Now, we don't know what I1 and I4 are, but we can express them in terms of the voltage drop across the resistor and the resistance of the resistor. So let's just substitute in the values that we have. So we know that this negative 2, that's negative 2 amps. And then we have plus what we have for I1. Well, the voltage drop across I1 is just going to be equal to the voltage on this side minus the voltage on this side. And the reason is we take the larger voltage and we subtract the smaller voltage. That's because current is flowing from a higher voltage to a lower voltage, so it comes with a bit of an assumption. But again, we've just assumed these directions, but that means we're just going to stick with it. So the difference in voltage is the higher voltage minus the lower voltage. So it's going to be VA, the voltage of node A, minus VB, which is the voltage of node B. And it's all over 1 ohm. Okay, so I4 is just going to be exactly the same logic. We've assumed that the current is going this way, so we think that VA is bigger than VC. So the voltage drop across it is just VA minus VC. And it's all over 3 ohms. We can just multiply each term by 3 to get rid of this 3 ohms that's in the denominator here, and rearrange and simplify this expression. Okay, so now we just need to reapply the same thing for node B. So we're going to apply KCL for node B. And again, we do the same thing. We look at what are the currents are coming in. So we have I1 and I3 are coming in, and I2 is flowing out. So when we set up our expression, we will take I2 as a positive. So we have I2 minus I1 minus I3 equals 0. We need to expand these out again, so we're going to take the voltage of I2, it's going to be VB minus 0. And again, we're assuming VB is higher than 0 because we are assuming the current is going this way, from the higher voltage side to the lower voltage side. So VB minus V0 is the voltage, and that is over the resistance, which is 3 ohms. So that is I2. And then we minus I1, or we subtract I1. So the voltage here is going to be VA minus VB over the resistance, 1 ohm. and then we're subtracting I3, and we're assuming the node, the voltage here at C, has a higher voltage because we're assuming the current is going this way. So we just have VC minus VB over the resistance, which is 2 ohms, and that's all equal to 0. Okay, so let's multiply these by the lowest common denominator, which is 6, and let's put it there, there, and there, and basically this is going to cancel out, so we get this whole thing times minus 3. The middle one is times minus 6, and this one is times 2. And then we can just distribute those out and simplify the equation. And then we just need to do this one more time for node C, so we're going to write KCL for C. And when we take a look, we have 3 amps coming in, we have I5 going out, we have I3 going out, and we have I4 coming in. So maybe let's scroll down a little so we have some space to work here. And we can just basically apply the same steps. So starting with I3, the voltage drop is VC minus VB. This is over the resistance, which is 2 ohms. And then I5, we have the voltage drop is VC minus 0 over the resistance, which is 1 ohm. And then I4, this is coming in, so it's negative. So we have VA minus VC all over the resistance, which was 3 ohms. And from the independent power source, we just have 3 amps coming in, and that's all equal to 0. So I think we're going to need more space still, that's fine. But we can also multiply these by the lowest common denominator, which is going to be 6. So we'll multiply everything by 6, that's a negative 6 there. And then these will cancel out, so this will be basically multiplied by minus 2. The 6 will stay in the middle, and this one will change to multiplying that term by 3. So we can just distribute those out, and we're left with one more equation. And at this point, we have 3 equations, so let's put a box around each of them. We have 1, 2, and 3, each with 3 unknowns. And so I'm not going to bother you guys with going through all of the work for this. You can either use back substitution, or you can set up an augmented matrix and solve it that way. But 3 equations, 3 unknowns, and we're able to find what we have for VA, VB, and VC. So we can label these back on the original diagram as well. And then we can see I3 here has to be switched in the direction, because right now we've labeled it on flowing from a lower voltage to a higher voltage, and that doesn't happen across resistors. So we just need to change the orientation here. I'll just draw over it maybe with a black arrow. It's actually going to the right, and then basically if you were asked to solve for the voltage drops and the currents in these resistors, that's a really quick operation that we can do as well. So V1 here is basically just going to be 5.38 volts minus 3.94 volts, which is 1.44 volts. V2 is just 3.94 minus 0, so it's 3.94 volts. V3 is just equal to 3.94 volts minus 3.69, so that's 0.25 volts. And then V4 up here is just 5.38 minus 3.69, which is 1.69 volts. And then V5 down here is just 3.69 minus 0, so it's also equal to 3.69 volts. And then if you wanted to solve the currents in each of these resistors as well, we can just use this rearranged version of Ohm's law. Just current is equal to voltage divided by resistance, and we have the voltage and the resistance for each resistor. So for example, I1 is just equal to 1.44 divided by 1 ohm, so it's 1.44 amps. I2 is 1.31 amps, I3 is 0.13 amps, I4 is 0.56, and I5 is 3.69. And then there's one final check that we can do to make sure that we've done everything right, is again, we can just consider KCL at some of these nodes. For example, if we want to look at the green node, we have 1.44 flowing in, and then 1.31 flowing out, and 0.31 flowing out. So the sum of these two flowing out is equal to 1.44. Over here we have 3 amps flowing in, and then 3.69 flowing out. We also have 0.13 flowing in and 0.56 flowing in. So all 3 of these that flow in, if you add them up together, they equal this one that's flowing out. So it looks like we've done it correctly, and yeah, hopefully that was a good example for you using nodal analysis. And yeah, thanks for watching. See you in the next video, and we'll start talking about probably supernodes or mesh analysis. I'm not sure. I'll see you there.